I want to look at the key for the quantum numbers exercise that you should have completed. In your reading and in the videos that you were assigned to watch, you should have learned about the three quantum numbers we're going to discuss here. N is the principal quantum number that describes the size and the energy of your orbital. It also determines the shell. L is your angular momentum quantum number. The video also called it the asymptotic quantum number. This is going to describe to you the shape of the orbital. M sub L, finally, is the magnetic quantum number that's going to describe to you the orientation in three-dimensional space for the orbital. Now, for the values of any set of quantum numbers that you write, it is only the value of n that you have any say over. You make a choice on the value of n or the shell that you're going to be describing orbitals for, and the rest of the quantum numbers are then based on that value of n that you chose. So the sets of quantum numbers will depend on what shell you're working with. So if we choose 1 for the first value of n, that means that we're going to look at all of the orbitals that are possible with respect to the first shell. So n was our choice, and we chose 1. That means that for the rest of the quantum numbers, when it comes to L, the only value of L that is possible is n minus 1. So 1 minus 1 is 0. So our first quantum number is n equals 1. Our second quantum number is L equals 0. That describes an orbital in the first shell, which we get from that n quantum number, and specifically an orbital in the first shell that is spherical in shape. So that is our 1s orbital or our 1s subshell. So we chose the value of n, and that determined what we can get for L, and that will also determine what we get for m sub L. M sub L's values go from negative L to positive L, and so in this case, because L is 0, the only possible value of m sub L is also 0. Given that that's the only set of quantum numbers that we can have when n equals 1, that describes a single orbital in three-dimensional space, so a single region in three-dimensional space where we have a high probability of finding the electron, and that orbital is going to hold 2 electrons. All of our orbitals will hold 2 electrons. We'll understand why that is when we talk about the m sub s quantum number. And so in total, in the entire first shell, that means that we can hold up to 2 electrons based on the set of quantum numbers that is possible when we select n equals 1. When n is 2, that means we're in the second shell. And so that means that n is 2, and the values of L that we have are going to start at 0 and go to n minus 1. So that's going to be 0 and 1 for our values of L. That means we're going to have two different shapes of orbitals that are possible in the second shell. So if we look first at n equals 2 and L equals 0. Whenever L is 0, that's a spherical orbital, so that's going to be an s orbital. This s orbital lies in the second shell. That means it's a little bigger, it's a little higher in energy, and the electrons that sit in this 2s orbital are going to be farther away from the nucleus than the electrons that sit in that 1s orbital. Because our L value is 0, the only possible value for m sub L that we have is also 0. So my second set of quantum numbers is n equals 2, L equals 0, m sub L equals 0. That means that in that 2s subshell, we've got one orbital that holds 2 electrons. Now in the second shell, we will also have a new subshell. We have a new value of L that's possible, and that's L equals 1. In the second shell, that's our maximum value of L. And so when L equals 1, that describes to us an orbital that has a particular shape in three-dimensional space, and that's going to be a dumbbell shape. So that will define our 2p subshell. Because L is 1, the values of m sub L that we can have start at negative 1, include 0, and go to positive 1. So 3 values. That means that we can have a dumbbell-shaped orbital with 3 orientations in three-dimensional space. So we'll have 3 different regions in three-dimensional space that we'll call 2p orbitals. Together, they'll give rise to our 2p subshell, and they'll hold a total of 6 electrons across those 3 orbitals. That means that across the entire second shell, we can hold a total of 8 electrons. In the third shell, we'll choose the value of n equals 3. The rest of the values are determined by that choice. So if n is 3, that means that my first possible value of L is 0. Whenever L is 0, I have an s orbital. This s orbital sits in the third shell, so it's bigger, it's higher energy, and it holds my electrons at a greater distance from the nucleus than my 2s orbital and my 1s orbital. When L is 0, m sub L can only be 0. such that the number of orbitals in that subshell is just 1, and again, that's based on your m sub l value. The total electrons in that 3s orbital is 2. When n is 3, I also have a value of L that is possible that will be 1. Whenever L is 1, that defines a p orbital, so a dumbbell-shaped orbital. This one sits in the third shell. Again, it's bigger, it's higher in energy, farther from the nucleus than the 2p orbital. And whenever I have a dumbbell-shaped orbital, I always have 3 of them. There are 3 orientations in space based on the quantum numbers where I have a high probability of finding the electron. So my values of m sub l are -1, 0, and 1. So in that 3p subshell, just like in the 2p subshell, I've got a total of 3 orbitals. They hold up to 6 electrons. In the third shell, my new set of orbitals is the d subshell. So the third shell is the first place where we see the d subshell. It comes from the fact that my maximum L value in the third shell is 2. 3 minus 1 is 2, coming from that n minus 1 maximum value as the possibility for L. Whenever n is 3 and L is 2, this defines a d subshell. My d orbitals have mostly 4 lobes, and then the fifth looks a little different because it has 2 lobes and a donut of electron density that goes around the middle. With an L value of 2, my values of m sub l that are possible start at -2 and go to +2. So I have -2, -1, 0, 1, and 2, giving me a total of 5 possible values. That means I'll have 5 different orientations in 3-dimensional space where I can have these d-shaped orbitals, where I can have a high probability of finding the electrons. I have a total of 5 orbitals that hold up to 10 electrons, so that across the entire third shell in my 3s, my 3p, and my 3d orbitals, I can hold a total of 18 electrons. As I move to n equals 4, I start with an L value of 0, as always. That means that this is going to define my 4s orbital. It has an m sub l value of 0, meaning that there's only ever one s orbital in a shell. It holds 2 electrons. When L is 1, that's going to define for me a 4p orbital. My 4p subshell will contain a total of 3 orbitals that each have a unique orientation in 3-dimensional space, arising from my 3 values of m sub l of -1, 0, and 1. 3 values mean I have 3 orbitals in that subshell that hold up to 6 electrons. In the fourth shell, I also have an L value of 2. This defines my d subshell. My m sub l values range from -2 to +2. That means I have a total of 5 orbitals, 5 unique regions in 3-dimensional space where I have a high probability of finding the electrons, and 5 orbitals will allow me to hold up to 10 electrons. In the fourth shell, I get my fourth set of orbitals, and those are the f orbitals. So in the fourth shell, my maximum L value is n minus 1, which is 3. Whenever L is 3, that defines my f subshell. My f subshell gives me the most complex shaped orbitals. These are orbitals that have mostly 8 lobes associated with them. And if L is 3, that means my values of m sub l start at -3 and go to +3, giving me a total of 7 values. That means there's 7 unique orientations in 3-dimensional space for my f subshell, and that f subshell can hold up to 14 electrons, such that across the entire fourth shell, I have a total of 32 electrons that can be accommodated among the 4s, 4p, 4d, and 4f orbitals. You should be able to write quantum numbers for all of the orbitals in the first 7 shells. These are the orbitals where we have the greatest probability of finding electrons. S, p, d, and f orbitals are the ones that you need to know. Once we get to the f orbitals, if we were to go to a higher value of L, the next value of L would be 4, which would give rise to a G subshell, followed by an L value of 5, which would give rise to an H subshell. But we only need the s, p, d, and f orbitals in order to place all of the electrons for all of the elements on the periodic table. You have 2 additional questions at the bottom of this handout, where the first one says, what is the orbital designation for the quantum numbers n equals 2, L equals 1? So right away, n equals 2 tells us we're dealing with the second shell. We should know from the exercise above that in the second shell, the only orbitals that are possible are going to be the 2s and the 2p based on the quantum numbers. Whenever L is 1, that's our p subshell. That's how it's been defined. So n equals 2, L equals 1 is going to be a 2p orbital. What quantum numbers can describe an electron in a 3p orbital? So right now, the fact that we're working with a 3p orbital means that n has been defined to be 3, L has been defined to be 1. That means that the m sub L values that are possible whenever we have a p orbital range from -1 to +1. That's going to give us a total of 3 sets of quantum numbers: 3, 1, -1, 3, 1, 0, 3, 1, 1.